is the minimum amount of quantum coherence? Let's say, what is the most mixed state that we can have that can still store a qubit? So this is of clearly a question of relevance in this noisy era of quantum computing. So let's say we need something like this. I think this is a reasonable minimum requirement, right? So we want our state to be able to store something that we can write as, say, a 2-qubit state. So we have some two states that are in principle that are orthogonal, psi1 and psi2, and we want to be able to write our density matrix in this form and this row. Okay, now this will be like play the question of our logical qubit and the psi, and the row is something, so it's something that has it's a mixed state with some finite entropy. Okay, and now protecting and storing these qubits has been a question that's maybe a bit not really new perspective, but something that should be, I think, discussed more today. And this has been studied in the context of decoherence-free subspaces already in the 90s. Noiseless subsystems, which are more exotic structures of this type, and so on, right? So, but can we go beyond now to more general types of quantum information protection? And here I'll take a Markovian perspective, but much of what I'll say can be generalized to non-Markovian situations. So let's say we have our system, whatever it is. It has its density matrix rho, right? And now I will write it like this. Okay, now let's say we model the influence of some dissipation, some external environment. And once I open it, so I model it with the Lindblad master equation, we have these L mu's that model the influence of the environment on our system. And what happens? Well, formally I can diagonalize this quantum Liouvillean, which gives me the time evolution. I have its eigenvalues and eigenmodes, right? Because now it's a super operator, so you have eigenmodes, not vectors. And I formally write down the solution to this equation. Now what's important here is that most of the eigenmodes will have negative real part, which means these are decay modes. If you wait long enough, these decay, these are dissipated away, right? So in principle, if you really want to do quantum computing in some circuit that, you cannot really use them because they'll exponentially quickly decay into nothing. However, you always have at least one state that has exactly eigenvalue 0. This is the stationary state. However, this stationary state in general will not be quantum coherent. It will not be of this form that I wrote down before. It will be, let's say, some thermal state or something like that. Now, we want our quantum coherence. If we want to use it, we want to be able to store it locally, which means we have to be able to access it in a way that is feasible realistically, right? If you have it all over your many body system, that's not very useful, right? So you want to be able to access it locally. That's a very important requirement that we have. Of course, now since the stationary state is time independent, it doesn't change in time, it has eigenvalue 0, it basically, it just stays what it is, and you have some, if it exists, right? I mean, it does exist, but if it's of this form, then it can store memory, quantum memory. Now the question is, when will it be of this form? That's a crucial question. And it turns out that there's a very simple requirement. First, obviously, we want it to be degenerate, right? So it should not be unique. There should be more than one. Why? Well, because this A that I used as the amplitude has to be, we have to be able to freely vary it, yeah. In order so we need at least 2 as our basis for such a state. That's like a minimum, that's a necessary requirement. And it turns out that it's quite a fairly easy set of general conditions when this happens for any quantum system of this type, and that's what we call a strong symmetry, right? So that basically means that your Hamiltonian and Lindblad operators commute with some unitary operator S, and then the degeneracy subspace, the kernel of your quantum Liouvillean, is spanned is basically its dimension is given by the number of distinct eigenvalues of this unitary operator S. And this allows to store quantum memory. Now, why is this a new perspective? Well, there is now an upcoming passive error correcting algorithm using this in cat qubits, which I like, obviously. So it's a bit something that's been proposed by these people, like, well, 8 years ago now, almost 8 years ago. But so it's basically an idea of storing in cat qubits, which basically means that you have bosons, right? So you have bosons, and you have crucially a 2 boson or 2 photon, whatever your boson is, this bit of process. So the Lindblads are A squared. And your Hamiltonian is whatever, some realistic bosonic Hamiltonian. I'm being very abstract here, but it's kind of more mathematical, but you can imagine any bosonic system you like. And of course now, since H realistic Hamiltonians are in principle parity symmetric, parity symmetry of the boson is a strong symmetry. And this allows you immediately to store quantum information. And indeed, it can be shown that this is extremely robust protection against bit flip errors. And indeed, now this will actually be used, I'm very happy to say, by Amazon soon, hopefully. Basically, the setup will be phononic crystals, as well, not photons, but phonons. But anyway, the same principle applies. And now, of course, this will probably be able to very nicely protect against quantum. Will be able to protect quantum memory. However, anyone who has worked a bit with these quantum computers that are available to us, like let's say IBM Q, probably knows that even though they have managed to get the gate error to be very, very small at each application of the gate, since if you want to do lots of gates, as you usually want to do for a useful quantum algorithm, the error, even though it's very small, it accumulates exponentially quickly. And this limits the circuit that you can do for a quantum computer quite considerably. And now gate error, I would say, is probably the major now issue in this era of quantum computing. So this setup will protect against errors in the memory, but not in the gate. If you make a gate error, the gate error will propagate. So what to do about gate error? Right, so the gates, actually, if you don't want any error, you want the dynamics of the gate gives to be perfectly coherent. So let's say now I will propose maybe some new ideas along these lines. Let's say now we want actually dynamics to be coherent. What does that mean? Well, mathematically, this means, again, that we have not just eigenvalues 0 that's degenerate, but we have purely imaginary eigenvalues, which will basically correspond to having coherent dynamics on some manifold. I give you some necessary and sufficient conditions, necessary with a caveat, but in realistic situations it's pretty much necessary. And it's kind of similar to the requirement from before. Now we want just, instead of having a unitary operator, we have a non-unitary operator. That's like a raising operator for a Hamiltonian, and that commutes with the Lindblads again, and their conjugate transposes. But and this exists, then your Hamiltonian will have purely imaginary eigenvalues, and then you can imagine having gate operations that are coherent in time. So maybe just let's say some open questions. Yeah, can we do something like this, but now for gates, so that we can have quantum computing gates that are in principle noisy, but still have some submanifold of coherent dynamics? This could work even at relatively high temperature quantum computing. Some other ideas may be coming from many-body physics, so non-equilibrium many-body physics. And that's an interesting question that I would like to ask people what they think about. So what is the connection between this quantum ergodicity theory that's being developed in the last 10 years and quantum computing? Now we know we have this eigenstate thermalization hypothesis, which basically states that a many-body system, if generic, whatever that means, many-body system will evolve into states that are indistinguishable locally in space from thermal states. So basically, let's say we have some quantum computer in principle, and we have, this is like our whatever hardware we have some local degrees of freedom, and we have some initial computational state, and let's say we have very good technology, we cool it to the ground state, and we encode our initial state in this setup. And now at t equals 0, we apply a gate, right? And now since a gate is basically a new Hamiltonian, the initial state is no longer an eigenstate. The initial state is no longer an eigenstate of our new effective Hamiltonian. In time, if we apply enough gates, we know that ETH, eigenstate thermalization, tells us that this shall be indistinguishable locally from a thermal state. So how to reconcile this with quantum computing? Is there something about thermal states that we don't understand that can actually locally help us to realize quantum information storage? Or do we need some sort of exotic hardware from a many-body perspective? Let's say that we have, for instance, time crystals. Yeah, time crystals, if you know, allow these coherent time evolution. Let's say time symmetry breaking, which basically means some sort of coherent time evolution that has some certain properties. Can these be used for quantum computing as a hardware? Or an interesting question is, people usually always talk about quantum this, quantum that, quantum coherence, entanglement. But I would like to understand what is the connection between, say, entanglement and classical correlation. How much of our entanglement that we study is really classical and how much is it really quantum? Should we more look towards computing Bell inequalities rather than that? Now, in this era, it would also be interesting to think about maybe, due to noisy quantum computers, maybe going back to mixed state quantum computing, which is known not to be universal, but still, you can do useful things with that. So maybe that's something that could be studied in the intermediate term. Anyway, I just had a bit of questions and perspectives here. So yes, that's all I wanted to say. Thank you.